Now that we know about QFT, the quantum Fourier transform, it's time to attack phase estimation. As a reminder, this is sort of step two in understanding Shor's algorithm based on everything that I've been reading about that. I think if you haven't, if you don't know what the QFT is and does and all that stuff, check out the videos. There's a playlist where I break that down in like 4 or 5 videos, I think, where I explain that intuitively, sort of what's the intuition behind quantum Fourier transform, even without any mathematics. Do that before you watch this video, I guess. I don't know. I mean, I'm recording that obviously, so I don't know. But I think the QFT is part of the quantum phase estimation. That's why it's probably you need to understand that. Let's see. I'm always starting with the IBMQ experience guide and see where does this take us. So let's get into this. Quantum phase estimation. Quantum phase estimation is one of the most important subroutines in quantum computation. Those are big words. It serves as a central building block for many quantum algorithms. The objective of the, so the, okay, that's good. The objective of the algorithm is this. So why this doesn't seem to render nicely? Maybe I should refresh the page. Let's give it a try. See if that renders better. Now, I'm curious about Shor's algorithm at that point. Oh yeah, now it renders better. So, given a unitary operator, U, the algorithm estimates theta in uh, in that's kind of your state vector, and then you apply U, and then uh, that seems super familiar to this whole thing about, like, you see, that's the good thing about breaking out different algorithms and then facing weird stuff. I was doing the video when I was doing the video about the I think it was something, one of the videos in machine learning, quantum AI, the one that was about gradients, and I think the sort of the GAN, building a GAN, I think it was. Check it out, because there I kind of encountered the topic of a Hamiltonian, and that was a bit shocking at the beginning for me. A bit was like, what the hell is that? And then kind of now I realize, so this is sort of a way you express mathematically, or a way you can implement your, yeah. So this is basically estimating theta in this. Here is an eigen. Here, this is an eigenvector, and this is the corresponding eigenvalue, whatever those words mean. Since U is unitary, all of the eigenvalues have a norm of 1. That's a really nice way of introducing. Okay, so that's a circuit, and that's the example. I mean, let's go through the circuit first, and I'll probably end up googling, see if I can find another explanation. But it's about estimating something, the phase. It's about estimating the phase, maybe it's something like given an operation or given a state. Yeah, maybe that's kind of given a state, estimate the phase. Because that's always something that's been confusing to me, is that when you take a look at a state, like, you've got those magnitudes, those amplitudes, whatever, those numbers there, which kind of, it's at the same time both the amplitude and the phase, they're all kind of encoded into that number. So it's like, why would you do that? Why wouldn't you just show what is what? Maybe you cannot, and maybe that algorithm is sort of a way to estimate that, kind of given a state, what's the phase, which I understand it's probably useful. Let's see, it's useful maybe because you can manipulate that to do other stuff, right? Because you can then maybe know, I don't know, I'm just having some thoughts about this. Is basically, if you know the state, the phase of your state, then you can, if you know exactly what it is, then you know which operation you need to apply in order to, I don't know, like, make a 180 degrees turn in that respect. So let's, you know what I mean. So if you know your phase is sort of 0, then you know you must apply 180 degrees if you want to get it the complete opposite phase in that sense. Maybe that's the I don't know. Maybe I'm completely wrong. Let's see. The general quantum circuit for phase estimation is the following. So, okay, so you're getting a bunch of qubits into a superposition. That's what's happening here. Then you've got like, okay, so those seem to be more like ancilla, and then this is the actual input to the problem. So that's your state. That's your state, and then you're applying gates. You're applying certain gates. So maybe a breakdown of those gates, but those are controlled. Okay. You see, it seems to me that like a month ago I would not have been able to understand that at all, and now actually thanks to breaking down some of those papers I seem to, because it seems to be the same pattern that what you have with what I saw in when I was breaking down the GAN. Go check the video, by the way. It's a really interesting one where th- because you're doing a control operation here and here and here, it's like almost like saying, okay, what if you do it or you don't do it, right? Because it's the Hadamard. It's gonna be basically be able to put you into that superposition of zeros and zero and one. So at the end of the day, when you get to point two, probably what you are gonna have is you're gonna have a state where you've gone through all the different possibilities of applying and not applying uh, each of those sub operations, if that's what it means, if those are simply the way you break down. Interesting. Hmm. Then you apply QFT, but it's not QFT, it's the inverse, right? That's cool. It's funny that the O'Reilly book actually, maybe they do this on purpose, because I had a hard time understanding QFT intuitively first, but then after reading the book I realized the inverse is easy to understand, but it all matches up. So okay, so because essentially what the inverse of the QFT is doing is trying to take whatever state you have and basically spread this in a sort of an even way. But how does this estimate the phase or tell you anything about it? Because then you're measuring. So then you're measuring each of those. I don't know. It doesn't seem impossible to decipher, but it's like I'm missing maybe the real purpose of this. So, as mentioned above, the circuit estimates the phase of a unitary operator. It estimates theta in this. Where is that? Blah blah blah. Set up this one set of qubit registers is in one set of qubit registers. An additional set of n qubits from an ancilla register. Okay, so that's what we said. This is sort of an ancilla, or like a. Then get into superposition, apply to the ancilla register. Yeah. Controlled unitary operations. We need to introduce the controlled unitary C minus 1 that applies the unitary operator U on the target register only if its corresponding control bit is 1. Since U is a unitary operator with eigenvector blah, such that blah blah, this means this. Applying all the n-controlled operations and using the relation. So that's just a vomiting of mathematics, where k denotes the integer representation of the n-bit binary numbers. The inverse Fourier transform. Notice that the above expression is exactly the result of applying a quantum Fourier transform as we derived. Really? Oh. So what they're basically saying is that, so what you're saying is basically this up until here, it's the same as the QFT. Kind of. So, but then you apply the inverse. recall the QFT maps an n-qubit state to blah, 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 blah. Replacing x by in the above expression gives exactly the expression derived in step 2 above. Therefore, to recover the state, blah, apply an inverse Fourier transform on the ancilla register. Doing so, we find this stuff. Then the above expression peaks near x equals 2 to the power of n theta for the case where 2 to the power of n theta is an integer measuring in the computational basis gives us the phase in the ancilla register with high probability. For the case when it's not an integer, it can be shown that the above expression still peaks near this with probability better than 40%. Okay. So we've got an example. Consider a 3-qubit quantum phase estimation of a 1-qubit register for 1-qubit state. Okay, that's a good example. Simple to reproduce. For this example, let us take the unitary matrix to be Z. Then the input state 1 is an eigenvector with eigenvalue -1. Blah, 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 blah. Hence, the theta is 0.5. Theta is 0.5. The theta of Z is 0.5. Okay. Yeah, that's a Qiskit implementation. At that point, we don't care much about it. Yeah, but that almost looks like. But why they're doing Hadamarts here as well? That's not in here. That's interesting. I'm trying to think what's the next step for me to understand this better. Maybe I should follow the example. Because at the end of the day, if I go and take a look at, let me see, if I take a look at, maybe I'll just open another tab with quantum, with the quantum experience. What I want to do is first of all, I want to try to, maybe let's build the example. Let's do the same with the QFT. I think that was helpful. I'm going to try to build the example and understand what we're doing. So it can be shown that I'm having trouble understanding the goal really fully, as in, like, is it really, because the goal is a bit abstract. Let me clear that up first. The goal is a bit abstract in the sense that it says it estimates theta, as in, it's like, is it the phase that okay, so maybe, so is this the phase change that the gate is creating? But how is that useful? Probably we need to then dive into Shor's algorithm to know how this is useful. So maybe I will not dive into that right now, but the idea here is, so it's telling us that Z has a theta of 0.5, which, if I recall and I go to the circuit composer, I think there's a gates overview here, and I think I can take a look at why I cannot, where's the Z gate? X, Y, Z. So, Pauli operators. I'm trying to see if I can verify. What? Pauli matrices. See if I can verify that. Because what Z is doing. No. I'll. What are the U? That's gonna. I'm trying to understand. I'm trying to figure out really if that makes sense. Uh, just because it makes me feel better. So what I'm trying to figure out is I'm trying to figure out. I'm trying to make sense of this of the statement here that says that the theta is 0.5 for the Z gate. And I want to do that by experimenting a little bit. So I'm just gonna put one register, one qubit. So if I apply a Z, I get that to 0. No, sorry, we'll apply this to the state 1 because it's gonna be easier to see. Come on. State 1, and now I apply a Z. So it takes me here, right? Now I want to replicate the same because I know the U3 gate. No, the U1. What was that? U. I know those exactly equivalent to the rotation through the Z. Okay, so I think we can use this U1 to check that, because if I go and take, I'm opening so many tabs that I'll get lost really soon. If I go quantum gates, stop scrolling. Multiple qubits. I want to see how do they implement those. Where is that? Where I can find that? Where I can find, it used to be somewhere here, where the U1 gate but if I basically if I now apply a U1 gate with the angle being pi, because here they say that this is supposed to be, I'm probably making you dizzy right now. This is supposed to be like 2 times pi I, and so it says theta is 1/2. So if I just do this, maybe I'm just making it too complicated, but what if I do this? No. Just do pi. That's where we're going to be. But then this still doesn't help me understand this quite a bit. I cannot find the I have a hard time finding the actual matrix. The actual matrix for the U1. Learn more. Yeah, but that takes me here, and that's not. I'll just IBM Q experience U1 gate. I think that takes me to the alt documentation. Could be. Mm, 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 mm. Okay, let's try another route. Basically, so they're saying the theta is 0.5. 0.5. Because I'm trying to understand how is this the phase or is this what is this? It's like the unitary matrix Z. So then they go ahead and they say set up a quantum circuit. We'll use three qubits: qubit 0 and 1 as ancilla, and qubit 2 as the eigenstate of the operation. So closing that, I'm going to the experiment again. So we're going to do use three qubits, and then basically we initialize this with 1. Good. Next, apply Hadamard gates to the ancilla qubits. Good. That's what we saw in there. Next, we perform the controlled unitary operations. So in this case, controlled unitary from Q1 is the identity matrix. What? What? Controlled unitary from Q1 is the control Z. Okay, so that we'll have to work out that bit in the next episode, probably. This bit here. But basically, what come on. What this is saying is that there's just a control Z needed here, and here it's a controlled unitary. So I mean, maybe to make it more obvious, I'm just gonna do like that. This is a control. It's just like a control identity or nothing, really, and then a control Z. Why is that? I don't know. And then we apply the quantum inverse Fourier transform to write the phase to the ancilla register. Okay. But what do we have now visually here is this. So it seems like what we're doing, but I still don't fully understand this, is we want to know what's the phase that's applied by the Z gate. So we break that Z gate down into something, which in this case is an identity and a control Z, and we apply it to this is our input, which is a qubit in state 1. But effectively what this has done is it has created sort of an encoded wave, almost like the square one, where it's like blue, blue, yellow, yellow. So now it's like, no, the other way. No. What am I saying? No. I don't know what is this. Okay. So this is literally 3, 4, 5, 7. And now we apply the inverse of QFT. And then we measure the ancilla qubit, but why is the inverse 1.57? because I thought to apply the inverse you'd have to. Let's just do it this way, okay? I'm trying to build the example and then try to understand what is going on here. So there is a control rotation of minus 1.57, and then there's a Hadamard and a Hadamard. Then there's a Hadamard and a Hadamard. Okay, and now what? And now we measure both, and there's another implementation. What the? What is this? But I'd say, okay, so this is, okay, so I'll run the example in another video, this one. So this is another example. We will see what happens to our estimate of a phase by using more ancilla qubits. Let's go from 2 to 3. And from, okay. So, but this I don't yet fully understand. Especially the result that we're going to get with highest probability. It's like 72% is, if we're measuring here, we're going to get a 2. It's a 1 and a 0, so we're going to get 2, which is basically what they, okay, this is what they say in here, right? So this is, okay, so this is the 2, okay. And then based on these 2, you can calculate theta. So then you do that, sort of not in the compute, not in the quantum circuit. So that's, you're looking for these 2 now, I understand, but okay, so you're looking for these 2. You're looking for the number 2. Why is that a good answer? I don't know. So, okay, I think it's enough for the very first attempt. It's more confusing than I expected, but I feel that I'm almost there to understand the problem actually itself. So, we try to estimate it's a 2, right? And our input was sort of the Z. So we have the following is, okay, so they are break down the Z into something which I don't understand why. And then the answer is it's 2. So that's like what you're estimating as in the phase. Okay. Because if I go this way and I have it here, and then I have a U1, and I say 2 times pi, what am I getting? That's not what I want. Did I say pi? That's what I want. Trying to find the relation between whether there's any sense in thinking that that's the kind of phase you're looking for, but it's not really. It's not really. But you're looking at a number that then is the phase 2. I don't know. But basically that seems to be the idea. It's, so you're breaking something down for some reason that it's equivalent to the QFT. So what you want to do is then you apply the inverse, so you get that kind of frequency. Kind of. Okay, folks, I don't know. I kind of feel we're getting somewhere, but it's still going to take a while. We've gone through the first example. I'm going to go through the second example in the next video, then try to make sense of all these, and then maybe look for some alternative explanation, see if we can make sense of all of what's going on here. Okay. Yeah, but that's what we said, right? So we get a 2, so that's kind of the expected answer. Okay, cool. Stay tuned for more on phase estimation and then Shor's algorithm.